Hello everyone, my name is Simran. My group members are Sourav, Rohan, Prithvi. Our topic for the presentation is vehicle dynamics of a car. Vehicle dynamics is a part of engineering that is primarily based on classical mechanics. The components of vehicle dynamics include automotive layout, steering, suspension, and traction control. For this assignment, we have chosen Maruti Suzuki Swift for the analysis. There are some values that we should be familiar with before we get into the calculations part. For calculating air drag and different moments, we need the vehicle dimensions. The height of the car is 1510 millimeter. The width is 1695 millimeter. The wheelbase is basically the distance between front and rear axle of the vehicle, and it is 2430 millimeters. The length is 3850. Track width is the measurement from tire to tire center, and it is 1490 millimeters. Overhangs are the length of a car that extend beyond the wheelbase at front and the rear. The front overhang is 820 millimeters and rear overhang is 600 millimeters. Here are the four figures showing all the dimensions of the car in the front view, top view and side view. Curb weight of the car is the weight without the baggage or the occupants, and it is 965 kgs. GVW is gross vehicle weight, and it is the maximum operating weight of the vehicle. It is usually specified by the manufacturer. In case of Maruti Suzuki Swift, it is 1415 kg. Weight distribution is 60-40 front and rear respectively. Weight distribution is also very important at deciding the brake force at the front and the rear wheels. And the center of gravity is at a distance of 1458 millimeter from the rear axle. Now we come to the wheel calculations. The front wheel has a dimension of 185 by 55 R16. The 185 means that the tire has a width of 185 millimeters, and 55 is the aspect ratio. That is, tire's sidewall height is 55% of the width, and R is telling how the tire was constructed. R is here used for radial. There are primarily three types of tires: radial, bias belt and diagonal. But nowadays 99% of the tires used are of radial type. And the other dimensions of the wheel include tire width, which is 185 millimeter, aspect ratio is 55, section height 101.75 mm, the rim diameter is 16 mm, rim diameter is 406.4 mm, tire diameter is 508.15 mm, and tire diameter is 20 mm approximately. The next part is suspension and braking. Suspension serves the purpose of keeping the occupants comfortable and a ride quality reasonably well isolated from road noise, bumps and vibration, also contributing to the vehicle's better road holding or handling, and braking for active safety of the vehicle. Because of the different constraints of the front and rear axles, different suspension systems are used. And in case of Maruti Suzuki Swift, the front suspension is McPherson strut, which uses the top of a telescopic damper as an upper steering pivot. And rear suspension is a torsion bar which twists in response to the motion of the wheels and absorbs the vertical movement. The brakes used in Maruti Suzuki Swift are different for front and rear wheels. The front brakes are disc brakes, while the rear brakes are drum.
Aspects, we come to braking condition now. As we all know, vehicle dynamics, braking conditions are a big part of vehicle dynamics. So we are trying to calculate the reactive forces acting on the front and the rear wheel and the stopping distance of a Swift, so that we may put those into account when designing a vehicle dynamic system. As we all know, the reactive forces acting on the front wheel is given by the formula B minus L minus mu h cos theta by B minus mu h into W, where each of the variables is as given. where B is the wheelbase, L is the distance of the center of gravity from the rear axle, h is the height of the center of gravity from road surface, mu is the coefficient of friction between road and tire, theta is the gradient of track, and W is the total weight of the vehicle. We have got these values from the manufacturer. Also, we all know that the force acting on the axles is as per the 60:40 ratio, but when actual braking happens, there is a change in the reactive force acting on the front and the rear wheels. That is what we'll be trying to find out. So let's talk about the stopping distance. Stopping distance is the actual distance that the vehicle will move once the brakes are fully engaged. So this is a very important parameter when designing a braking condition of a vehicle, because this will actually decide how much the vehicle will move after you put on your brakes. So this we'll get by the formula which is given by A by G equal to mu into B minus L into cos theta divided by B plus mu H minus sin theta. As we have talked about the variables involved, and the only other variable used is A, which is the deceleration rate which we are trying to find, and theta as usual is the gradient of the track. We also need to use the equation of motion v square minus u square equal to 2as to get our desired result. So we've used these formulas to find out the braking conditions for a Maruti Swift. Okay, and we after doing our calculations, we have got the reactive force acting on the front wheel as 10,058.75 Newton and acting on the rear wheel as 3,808.25 Newton. So if you notice here, if you add these two, the reactive forces acting on the front and the rear wheel, it roughly comes around to 13,867 Newton, which is equal to the gross weight of the vehicle. Also, the maximum rate of deceleration as obtained from the formula is given by 5.8896 meter per second square. We've also tabulated the stopping distance for the different speeds at which the vehicle might be moving. For example, as you see from the table, if the vehicle is moving at a constant speed of 50 km per hour, the stopping distance is fairly 16.36 meter. Also for 100 km per hour, it's 65 meter. For 150, it's 147.38 meter. And the top speed of the vehicle, 165, it is approximately 178.63 meters. So these are the parameters we have taken into account when designing the vehicle dynamics of a system.
Moving on to tractive force. First of all, what is tractive force? Yeah, as you can see, the tractive force is the force applied between the tire and the road surface to move a car. So for a vehicle to move, you need tractive force. So the maximum permissible traction that can be applied, it depends on two factors. Firstly, the weight of the vehicle and the coefficient of friction between the tire and the road surface. So for the maximum tractive force, the formula is the product of the coefficient of friction and the normal force, which is the weight of the vehicle. So the higher the weight of the vehicle and more the coefficient of friction, higher is the tractive force required to move the vehicle. Since maximum torque multiplication takes place in the first gear, so the maximum tractive force that the vehicle can generate is, in most cases, it's in the first gear. So there are three types of tractive effort or forces available. That is the starting tractive effort, which is to overcome the inertia. And the next one is the maximum tractive effort. That is generally we get the maximum tractive effort in the first gear to overcome inertia. In most cases, the maximum tractive effort is equal to the starting tractive effort, and the continuous tractive effort, which is required to move the vehicle indefinitely in the other gears. These are the specifications for Maruti Suzuki Swift, which has a 1.3 liter diesel engine with a 190 Newton meters torque. The powertrain efficiency is 0.8, and the gear ratios and the transmission ratio is given, and the rolling radius of the tire, which is 185 by 60 R15 tire, it's 0.254. The surplus tractive effort available is used for acceleration. So calculating the tractive force, the tractive force can be calculated theoretically as well as by conducting tests experimentally. So theoretical calculation, we have the parameters: engine torque, the powertrain efficiency, the transmission ratio, and the drive ratio. The drive ratio is responsible for putting on the torque to the wheels, and of course the rolling radius. This is the formula, and we have calculated the tractive effort available in first gear So we get it as 9,308 newtons, 9,308.7 newtons, and the maximum tractive effort, which depends on the coefficient of friction and the weight of the vehicle, is approximately 9,706.9 newtons. You can see both the values are similar, and that says that the maximum tractive effort is generated in the first gear. Yeah, coming to aerodynamic resistance. First of all, imagine you are at 100 kilometers per hour and you bang a brick wall. What is going to happen? The metal and the glass, everything is going to shatter. The metal is going to deform. So we should assume air as a layer of wall. So at high speeds, when the vehicle cuts through the layer of air, a lot of drag is generated. At low speeds, yeah, you can ignore the drag because it is not substantial. So at high speeds, it makes a lot of difference. So as you can see, as the designs have evolved compared to the 60s and 70s, the boxy shapes have given way to curvy edges and smooth contours so that the flow of air, the resistance generated is reduced. The aerodynamic resistance is composed of three factors, and the main important factor is the turbulent flow around the vehicle, which accounts for 85% of the drag. Then the friction of air over the vehicle body, the sliding friction, which accounts to 12%, and the vehicle component resistance accounts to 3%. Components in the sense the rear view mirrors, external rear view mirrors, the mud flaps, the grille, the headlamps, etc. Now calculating it under atmospheric conditions, taking the density of air as 225 kilogram per meter cube, and the drag coefficient of Swift is 0.32. The frontal area is 1.8 meters square. Now calculating the aerodynamic resistance at 60 kilometers per hour. It's not a very high speed, yeah, but yeah. So calculating the aerodynamic resistance, we get it as using the theoretical formula. The density, the coefficient, drag coefficient, the frontal area, and the velocity, we get it as 97.2 newtons.
Aerodynamic resistance, we are going to shift to rolling resistance, which is another anti-motion resistance. So what is the coefficient of rolling resistance? It is the resistance for a tire profile on the road, whatever we choose, whatever combination we choose, the resistance to rolling of the vehicle. So there are different values for different concrete roads are there, gravel roads are there, loose sand is there. So the coefficient of rolling resistance are different for each of these surfaces, which means that it is 0.2 to 0.4, which is very high for a loose sand road surface, but it is very low for a tar or asphalt road, which is normally the case in urban roads. So we have assumed the CRL value to be 0.2, which is loose sand coefficient of rolling resistance for calculation. So we know the weight of the vehicle, which we have assumed to be a Swift, is 13,867 Newton, and we get the total rolling resistance offered to the motion of the vehicle, which is equal to 2,700 Newtons. So moving on, we are going to calculate the maximum gradability of a vehicle. So when a vehicle moves upslope, there is a limit to the slope it can actually traverse. So there is rolling resistance, there is aerodynamic drag, and the vehicle has to overcome this in addition to the gradient resistance, which is mg sin theta basically of the vehicle, which is the component acting along this slope. So we are going to find out the gradient resistance. We know that the maximum tractive force, which we have calculated earlier, is equal to the aerodynamic drag, the rolling resistance, and the gradient resistance. So for the vehicle to at least have a motion, pure rolling motion, the maximum tractive force should be equal to these three resistances to the vehicle, offered to the vehicle. We know the maximum traction is 9,308 Newton, which we have calculated earlier. The aerodynamic drag, which is 97.2 Newton. And the rolling resistance, assuming CRR to be 0.2, we have got 2,773 Newtons. And we get the total gradient resistance that the vehicle can offer is 6,438 Newton. And from that, since we know that it is basically the sine theta component of the vehicle weight, we find that the gradability of the vehicle is 27.66 degree. Now, it is very important to note that we have assumed CRR to be 0.2, which is not the case for most uphill driving, where the roads should be in a good condition, and the coefficient of rolling resistance should be much lower, say around 0.05, 0.02. And for a loose sand road profile, we get a gradability of 27.66. Again, this is an ideal case scenario in which there are no other resistances offered and the transmission efficiency is very high, for which we get 27.66. Okay, so moving on to longitudinal load transfer. Longitudinal load transfer is basically when the vehicle is moving along a direction, weight transfer along the motion of the vehicle. So it can either be rearward or it can be forward. So when a vehicle is accelerating, suppose it is at a uniform velocity at the initial position, when it starts accelerating, what happens is the vehicle is speeding away. So there is a change in state of motion. While the vehicle should have remained rearward, what happens is the vehicle is moving ahead of its position. So there is a rearward weight transfer because of this option. And this exact opposite happens during braking. So suppose the car is at 20 km per hour initially. When it is braking, it should have remained at 20 km per hour, but what happens is it comes to a stop, which means that the weight of the vehicle shifts forward. So there is a forward weight transfer during braking and there is a rearward weight transfer during acceleration of the vehicle. And the values can be calculated using this formula, which is acceleration of the vehicle into the weight into the center of gravity divided by the wheelbase. So larger the wheelbase, smaller is the weight transfer. And similarly, higher is the center of gravity, higher is the weight transfer of the vehicle, whichever be it, rearward or forward, during acceleration or braking. We have taken an example here. So this is a race car with the weight distribution shown: 521 pounds in the front axle, 1239 in the rear axle, and the total weight is 1760. So we have calculated the longitudinal load transfer. The acceleration is 0.8 g because it should be high because it is a race car. 760 pounds is the weight of the vehicle. 13 inch is the height of the center of gravity from the road surface, and 100 inch is the total wheelbase. And we get 183 pounds, which is acceptable because the wheelbase is small and the height of the center of gravity is really small, because for a race car it has to be grounded, like the center of gravity should be as much closer to the ground as possible. Okay, and the total weight transfer we find is 183 lbs towards the rear wheels or the rear axle, because the vehicle is accelerating at this point. We have also calculated two certain values. Keeping in mind it is a Suzuki Swift, during acceleration we know from the 0 to 100 km per hour value of time we get a 0.2 g acceleration rate, and we find that there is a 81 kg weight transfer during acceleration towards the rear wheels. Similarly, during braking, for maximum braking condition we get around 5 to 6 meter per second square deceleration rate, and hence we have assumed 0.6 g of deceleration, and there is a 244 kg weight transfer towards the front wheels. And this is longitudinal weight transfer, which means that there is a weight transfer towards the front or towards the rear axle during motion.
From longitudinal load transfer, we are coming to lateral load transfer. So lateral load is the same as longitudinal load transfer, except the axis is shifted by 90 degrees. So longitudinal is basically pitch, whereas lateral is roll. So in lateral as well, like in longitudinal, there's a centrifugal force. There's a moment acting at the CG. So basically this moment acts due to the centrifugal force. When you're cornering, there's a centrifugal force acting through the CG, which tends to throw the vehicle away from the turn, away from the turn. So tangential to its intended path. So this centrifugal force is resisted by the lateral forces developed by the tires, which is the cornering force. That depends on the vehicle geometry and the loading on the tires. So the basic load transfer equation applies again as it applies in longitudinal weight transfer. This is lateral acceleration, that is what you'll get at that is dependent on the radius of the turn and the velocity at which the vehicle is taking the turn, into weight on that axle, into CG height by the track width. So CG, these values we have for the Swift, which we have calculated later on. So you can see a model here, which is of a race car, which has a lateral acceleration of 1.4 g, which is normal for F1 cars or race cars. So as you can see, there's a 1.4 g lateral acceleration. At that lateral acceleration, the load transfer is 1.4 into 1080 pounds is the weight on that front axle. This is the front axle, and the vehicle is taking a left turn, and the load transfer from this equation is 328 pounds. So 328 pounds is very acceptable, quite acceptable for a race car. Also we find the cornering force to be 1400 pounds. So this is for the race car. You can see the CG is 13 inch and the track width is 60 inch, which is the CG is very low and the ratio is also low. So you can keep the load transfer down. Now moving on, we go to cornering force or tire force. This is the side force generated by the tires during cornering. So this is the force that keeps the car into the turn and negates the centrifugal force. Without this force, the car would just understeer and be thrown out. So this is generated by the tires. As you can see here, this is the graph for the cornering force versus vertical load. Cornering force is directly dependent on the vertical load on the tires. So as you can see, the graph, the rate decreases as the vertical load increases. There's a tire force. Earlier it's sort of linear, then it kind of fades away. So you can this is the equation for a lateral acceleration. So now moving on, this is what we calculated for the Swift, this would be generally for any hatchback. As you can see, the CG height for the Swift is 0.7 meters and the track width is 1.49 meters. So for those values and the radius of a curve of 100 meters, which you could say a normal turn on any highway. For reference, freeway curves are around 200 meters. So you can see from these, we calculated for 3 speeds, which is 60, 80 and 100 kilometers per hour. And the lateral accelerations for these are as follows. So at 60, the lateral acceleration is 0.3 meters per second square, and you had a weight transfer of 119 kg. So say the car is taking a left turn at 60 kilometers per hour on a 100 meter radius curve. You'll have when you're taking a left turn, you'll have weight from the inner wheel going to the outer wheel, that is 119 kgs goes to the outer wheel, and the cornering force of the total the total of the inner and outer wheel is 975 kgs. And now in a steady state, the cornering force, when you have, for a Swift, we have a weight acting on the front axle as 850 kgs. So for at steady state, the load on both the tires will be 425 kgs each. And at 425 kgs, from this graph, what we get is the cornering force is 1043 kgs, while when you see after there's a load transfer, the cornering force is reduced. So as you can see, as the cornering force is directly proportional to the loading on each tire. Now again, for 80 kilometers per hour, we calculated around 200 kgs of weight transfer, and again the cornering force is reduced even more. So there's a trend here. As the speed increases, the cornering force is decreasing with the speed for that particular turn. Yeah, that's it.